Okay, good. For example, in random order streams, when the edges of the graph are presented in a uniformly random order, one very often uses the randomness of the stream to perform statistical estimation to sort of guide this exploration process. And somehow recently, the rule of thumb that has emerged is that if the optimal algorithm for our graph analysis problem amounts to storing a subgraph, or at least even if this subgraph is very adaptively and carefully chosen, then one can often get a tight or nearly tight lower bound using Boolean Fourier analysis. And in this talk, I will mention some of the recent works and the principles that go into this. Good. So what are the problems that we're interested in? Well, first, we'll be interested in the classical problem of testing bipartiteness. So here, the foundational work of Goldreich and Ron from 2000s shows that one can tell if the graph is bipartite or epsilon far from bipartite in about n to the 1/2 queries to the input graph. And so a natural question to ask here is whether or not it is possible to translate these algorithms, which generally are used on are based on the idea of running about n to the 1/2 random walks of polylogarithmic length and counting collisions into the streaming model of computation. The hope would be to achieve also n to the 1/2 space complexity. Or, for example, perhaps we have a, say, bounded degree graph that is shared across multiple parties. Each party sketches locally their part of the graph, sends this to some referee, and the referee wants to know the number of triangles in the graph approximately. Or perhaps we are in the random order streaming model. We're getting a randomly ordered stream of edges of a graph, and we want to approximate the number of connected components. A beautiful recent work of Peng and Zoller shows that you can do this to a good precision in a surprisingly low amount of space. Or perhaps we're given the input, given a randomly ordered stream of the edges of the input graph, and we want to estimate the page rank of some subset of vertices or generate random walks. Good. So in all of these questions, the best known algorithmic results essentially store carefully chosen, adaptively chosen subgraphs, and it is possible to obtain nearly tight lower bounds using Fourier analytic techniques. So that's what I will talk about. Good. So the Fourier analytic, are there any questions at this point? No
questions, anyone? No, be good.
All right, good. Okay, so these Fourier analytic techniques are inspired by the foundational work of Gawinski, Kempe, Karinidis, Raz, and de Wolf on the Boolean hidden matching problem. So I will first talk about this problem, which is a two-party communication problem, and then I will talk about how these techniques can be leveraged to analyze multiplayer games. And this will lead to streaming lower bounds. Good. So the Boolean hidden matching problem is a two-party communication problem. The two parties are Alice and Bob. So Alice gets as input a binary string x in 0, 1 to the n of length n. One can think of this string as encoding a bipartition of the vertices of some graph. And it's good to think of this string as uniformly random. It will be that in the hard distributions. Now, Alice looks at the string x, compresses it into some message m, and sends the message to Bob. Bob, on his side, has in hand a matching m. Think of it as a uniformly random matching of linear size in the number of vertices of the graph, and labels w's on the edges of the matching. So here these labels are shown in red, so there's zeros on both of the edges. Good. There will be a yes case and a no case. In the yes case, the labels are exactly, the label of an edge E equals UV is exactly the XOR of the bits of the corresponding endpoints. In the no case, the labels are just random garbage, so uniformly random 0 1s. And Bob's task is, given the message from Alice and the matching and the labels, distinguish between yes and no. Good. So what is a natural protocol for this? The natural protocol to solve this problem is Alice simply samples uniformly at random about a square root n coordinates of x and sends the corresponding bits to Bob. By the birthday paradox or the birthday phenomenon, with a good constant probability, there will be at least one edge such that Bob knows both of the bits on both endpoints, and so Bob can simply check if he is in the yes case or no case. And Gavinsky, Kempe, Karinidis, Raz, and de Wolf showed that this is basically tight, so omega n space is needed. All right, so how do they show this? The question to ask oneself here is the following. If we put ourselves in Bob's position, we want to understand what the distribution of the bits of the parities across the edges of Bob's matching is conditioned on Alice's message. All right, so conditioning on Alice's message makes X, which is a priori uniformly random binary string, uniformly random on some subset of the Boolean hypercube. Here's the subset pictured in red. And if Alice sends S bits, and think of S as smaller than square root n, then the subset is pretty large. It occupies a largish fraction of the Boolean cube. So let F denote the indicator of A. Okay. The main observation here is that if we think of an edge ij in Bob's matching, then the chance of guessing the parity xi plus xj is basically 1/2 plus the absolute value of the normalized Fourier coefficient of Alice's message at ij. Okay, so here's the definition of the normalized Fourier coefficient. It's just the expectation of the parity -1 to the x dot z over x uniformly random among those bit strings that are consistent with Alice's message. Good. And for example, just to argue that Bob cannot guess any of the bits, any of the parities on his edges, it would be enough to show that in expectation over the random matching, the sum of squared Fourier coefficients of the corresponding pairs, pairs of vertices in the matching, is small. And indeed, this turns out to be the case. One first, as per Gavinsky and all, one first notes, this is a consequence of hypercontractivity, that the sum of squared normalized Fourier coefficients over of a largish subset of the Boolean cube, one that occupies at least a 2 to the minus s fraction of the cube, is bounded by order s squared. So think of s as basically the communication, the number of bits communicated by Alice. And that turns out to be key. So this holds for any compression strategy, and one can verify that for the trivial compression strategy, that just plain text sends square root n bits from Alice to Bob. Indeed, this is true. Basically, the normalized Fourier transform of a pair ij is 1 if Alice transmitted both bits to Bob and is 0 otherwise. That's 1 in absolute value. So indeed, the sum of squared Fourier coefficients over all pairs is just communication squared. Great. Then Gavinsky and others note that the probability that any given pair belongs to the matching is 1/n, roughly, and hence in expectation of the sum of squared Fourier coefficients over the edges of matching is communication squared by n. And if communication was less than root n, then Bob cannot really guess the parity of any edge in the matching. Okay, great. So of course, this doesn't really show that the distribution that Bob observes on the distribution of Bob's XORs is close to uniform, but a similar higher order version of this analysis establishes this. Okay, great. So this is the Boolean hidden matching problem. Or any questions so far? Okay, seems not. All right. Good. So how can we use the Boolean hidden matching problem for streaming low bounds? This problem initially was introduced to exhibit a separation between quantum and classical one-way communication complexity, but now we would like to use it for streaming. And in streaming, very often one needs multi-party communication problems. So I would like to first talk about this question of testing bipartiteness. Indeed, suppose that we're given edges of a graph G in a stream, and we want to understand if the graph is bipartite or epsilon far from bipartite. Or even more generally, perhaps we want to approximate max cut in the streaming model of computation. Okay, good. So before I talk about max cut, it will be useful to define a somewhat different communication problem It sort of looks like the Boolean hidden matching problem, except there is no Alice and there's many Bobs. We call it the implicit hidden partition problem. This was introduced in the joint work with Sanjeev Khanna, Madhusudan, and Ameya Wellinger. And so it's a T-player communication problem. There's T players. Think of T as a large constant. Every player receives a matching of linear size, a random matching, together with labels W on the edges of the matching. So player 1 receives a matching M1, labels W1, here they are shown in red, and posts some message about these labels on the board, on a common board for the subsequent players to see. So this precedes player 1, 2, and 3 speak in turn, and the last player should output the answer. Okay, the answer to what? We want to be distinguishing between two cases. In the yes case, there exists a partition X. Here is the partition shown on the slide. These are the bits on the vertices shown in black. In the yes case, there's a partition X such that the labels are consistent with the bipartition for all the matchings MT between 1 and capital T. And in the no case, there is no such partition. Of course, we're interested in a distributional version of this, where the partition, this hidden partition in the yes case is random, and in the no case, the labels are just random. And in the yes case, they're all consistent with this partition. Good. What are the matchings? The matchings, as before, are also random and of linear size. Good. So here the matchings given to all the Bobs overlaid on top of each other. Okay, great. So what does this have to do with max cut? Here's the reduction. Let T the number of players to be some large constant depending on the approximation ratio for max cut that we want. My reduction will produce in the yes case a random bipartite graph with a very small number of multi-edges with a large constant expected degree, and in the no case a very non-bipartite random graph with the same expected degree. The reduction is very simple. The Tth player simply looks at their matching MT and feeds into our streaming algorithm those edges of the matching that have ones written on them. Okay, so in the yes case, all of these edges will satisfy, will be consistent with the bipartition. So the union of produced graphs will be bipartite. And in the no case, the union of produced graphs will be very far from bipartite. It will be essentially very similar to a random Erdős-Rényi graph of average degree 1/epsilon². So that's very, very far from bipartite. Good. So to prove hardness of streaming max cut, it suffices to prove a communication complexity lower bound for implicit hidden partition. And indeed, such a lower bound has been proved. First, we showed in a joint work with Sanjeev Khanna and Madhusudan that any T-player protocol that essentially solves implicit hidden partition requires square root n over poly T communication. Okay, so the dependence on n here is only square root, but the dependence on T is inverse polynomial. Right, and this proof basically follows from Boolean hidden matching. In our implicit hidden partition problem, there are capital T copies of Bob, and there's no Alice, but one can add Alice, who speaks first, and then note that essentially Alice needs to get advantage at least 1 over number of Bobs in one of these problems, and hence by standard Boolean hidden matching analysis, a square root n over poly T communication lower bound follows. One should note here that this is tight. This is tight for T polylogarithmic in the number of vertices of the graph, because indeed, if T is polylogarithmic, that we can use the techniques of Goldreich and Ron to distinguish between these two cases. Good. On the other hand, if T is constant, then the following bound with Dmitry Krachun gives a better result. We show that any T-player protocol that solves implicit hidden partition requires n over T to the T communication. So here the dependence on T is exponential, and this is also tight, but the dependence on n is linear. Good. So let me just say a few words about how this proof goes, and then move on to other questions. Good. So let me remind you that we're looking at the following distributional version of the problem. There's a hidden bipartition X, which is uniformly random, and capital T bobs, each of which receive a random matching with corresponding labels. In the yes case, the labels are consistent with the random bipartition. In the no case, they are just random. Good. So what we would like to prove is the following. Suppose, for example, we look at one of the players, let's say player number 4. And from the perspective of player number 4, the following happens. Conditioned on the messages from players 1, 2, and 3, that is the red, blue, and orange players, the hidden bipartition X, if it exists, and let's assume that we're in the yes case, is uniformly random in the intersection of 3 sets, the red, blue, and orange. On the hypercube, all of these sets are pretty large. They correspond to a large density sets because there's not so much, the amount of communication by assumption is low. And the amount of communication is S here. Good. So let F1, F2, F3 be the indicator functions of these 3 sets. And let H be the product of these indicator functions. H is the indicator of the intersection. So in order to prove that from the 4th player's perspective, the distribution of the bits on their matching, the parities across the edges of their matching is close to uniform, it is enough to sort of mimic the proof, the Boolean hidden matching analysis, and upper bound the sum of squared Fourier coefficients of various Hamming weights. That's exactly what would correspond to Boolean hidden matching. And the question, however, is how to do this, because we need significantly stronger bounds here. Essentially, we need a mechanism to lift better bounds on the Fourier spectrum of individual indicators to bound on the Fourier spectrum of their product. Right? And indeed, here, every bob only gets access to this bipartition in a restricted manner. Every bob learns only about parities over the edges of their matching. So one can prove better bounds for the individual F tildes that give us a n lower bound as opposed to square root n. But how does one do this for the product? And here the idea is to use the convolution theorem to analyze how bits of information from different players get combined. By the convolution theorem, the Fourier transform of a product is the convolution of Fourier transforms. And this roughly holds for these normalized Fourier coefficients under good conditions. And that's exactly what we do. So somehow the intuition behind this is very natural, namely that the use of the convolution theorem allows us to understand how information from different bobs gets combined. Okay. So for example, here, if the red player transmitted some information about parities of X across the red matching, and then the second player transmitted information about the parities of X across the blue matching, then they can combine their knowledge to learn about, let's say, XA plus XD. So neither of them really knew anything about XA plus XD, but both of them together do, because there is a path A, B, C, D from A to D. And the fact that one can combine different matchings into longer paths is exactly captured in a robust manner by the convolution theorem. Good. So basically, the main contribution here is to analyze the convolution of these individual indicator, the Fourier transforms of individual indicator functions for a large number of players. And the main technical innovation here is the idea of not sticking with the standard L2 squared upper bounds on the Fourier transform of the individual players' indicators, but rather to use the L1 norm instead. This is significantly more robust under convolution, and basically lets us push this through. One very interesting thing to note is that a recent work of John Callagher and Parech, appearing in Fox 22, shows that these L1 upper bounds on the Fourier spectrum effectively seamlessly translate to the quantum setting. So they prove the lower bounds for approximating max cut for quantum computers, essentially extending our results, showing that no non-trivial approximation to max cut with sublinear in the number of vertices space can be achieved even with a quantum computer. So this is very interesting, and it seems related to the fact that basically Boolean hidden matching admits a polylogarithmic quantum communication protocol, whereas the Boolean hidden hypermatching, when the edges have larger arity, already does not. So somehow there's a L1 to L2 gap, and this gap is exploited by this very, very cool new result. Good. Okay. Good. So that's what I wanted to say about the idea of using the Fourier analytic methods of Boolean hidden hypermatching paper together with the convolution theorem and bounds on the L1 norm of the Fourier transform to analyze multiplayer communication games. This idea has been useful in other settings beyond max cut, and of course it has been useful quite a lot for constraint satisfaction problems. But let me just quickly mention subgraph counting through sketching. So here, the question is the following. A bounded degree graph is shared across multiple players, and every player individually compresses their share of the input, and they all simultaneously send it to some coordinator, who then should output the number of triangles in the graph. Good. Using Fourier analytic techniques, it is possible to get tight bounds, as this is from a paper with Joan Callagher and Eric Price, on the sketching complexity of triangle counting and subgraph counting in general. In particular, we show that if the input graph has t triangles, then number of edges m over t to the power 2/3 is a tight bound on the size of the sketch needed to approximate triangle counts. Okay, so note that if you haven't seen triangle counting results before, most of them come in this flavor. It is some number divided by some function of the triangle count. Indeed, it is easier to find triangles in graphs where there are a lot of them. Okay, but somehow the interesting tidbit to take away here is the following. So suppose that we want to distinguish between bounded degree graphs that have the maximum possible number of triangles, that is, number of triangles is n, and have no triangles, then this can be done in using a sketch of size n to the 1/3, and this is sharp. So that's something that one can establish similarly using the convolution theorem. The result generalizes beyond triangles and beyond graphs to hypergraphs, but let me just give you a sense of the communication game that comes in. And I will not talk much about the analysis. The communication game is the following. There will be three parties, Alice, Bob, and Charlie, and a three-partite graph pictured on the slide. The three parts are connected by matchings. There is the red matching, Alice is matching MA. There's the green matching, Bob's matching MB, and Charlie's blue matching. These matchings are random, subject to the constraint that their composition is the identity. So this is really just a union of disjoint triangles. Good. Then the edges of the input graph come equipped with bits. So these are, again, random bits. Here they are shown on the slide. We call them XA, XB, and XC. They are uniformly random, subject to the following constraints. In the yes case, they add up to 0 across all the triangles, and in the no case, they add up to 1 across all the triangles. Okay, so for example, this game is in the yes case. Good. And then Alice, Bob, and Charlie simultaneously send some message about their edge set to some referee, and they should basically figure out which of the two cases they're in. So one can prove that n to the 1/3 communication is needed to solve this problem. And the optimal protocol here is again to store a subgraph, except that in this case, this is the optimal thing to do is to store a random vertex-induced subgraph. The players have to coordinate to sample a random vertex-induced subgraph. Okay, good. So that's all I wanted to say about this. In the remaining 10, 15 minutes, is this correct? Yeah, 15 minutes. Great. Okay, I will. Are there any questions? No. All right. Good. I will talk about some of our recent work that takes a different approach to using Fourier analysis for streaming lower bounds, and in particular, here we show how to analyze a game with an effectively infinite number of players. So this is a different approach to using the convolution theorem. And here, the problems that I will care about are as follows. First, suppose that we are in the streaming setting, and our input is a stream of edges of some graph G in a uniformly random order. We want to approximately compute the number of connected components in this graph. So a very nice result of Peng and Zoller from Soda 18 shows that one can approximate the number of connected components in such a graph using up to an epsilon and additive error, using space, which is essentially only a function of the precision epsilon. So 1 over epsilon to 1 over epsilon cubed. Good. One should note here that essentially to approximate the number of connected components up to an epsilon and error, one should count the number of connected components of size up to epsilon. So this is intuitively about learning the structure of constant size connected components, of how many of them there are. And Peng and Zoller show that you can do this. You can get statistics of the number of connected components of size up to 1 over epsilon in space exponential in 1 over epsilon. Okay. Now, another related result here is our recent result with Callagher and Price on generating random walks in randomly ordered streams. The question is this: we're given a randomly ordered stream of edges of a graph G, and we want to generate S walks at random walks of length L, started at uniformly random vertices in the graph. And of course, one can allow for some total variation distance error. There are some details here. And we show that one can basically solve this in using space exponential in L squared, so exponential or worse in the walk length, times the number of walks to be generated. And we want to understand why such long-range exploration appears to require space exponentially large in the depth of this exploration in randomly ordered streams. Good. So that's the question that I would like to resolve. To be a little bit more precise, I will not care about counting the number of connected components in a graph, but rather I'll be interested in the component finding problem. It's a related problem. In this problem, I want to, I'm given as input the edge set of a graph G permuted randomly, and I want to find a connected component of size at most L. L is some parameter given to me, assuming that there are many such components. If one squints and looks at the result of Peng and Zoller from Soda 18, then one realizes that they basically design a component finding primitive that runs in about L to the L cubed space and then use it for component count estimation. Good. Are there any questions about the problems?
No.
All right.
Go ahead.
Good. Okay, so basically, to this effect, we introduce the following communication problem. It's essentially a streaming problem, so we call it streaming cycles. In this problem, our input is a disjoint union of n by L cycles of length L. So here they are pictured on the stream. These the edge set of this graph, this disjoint union of cycles, will be presented to us in a random order. And we'll not just get the edges, but rather the edges will be annotated with random bits. So here the random bits are shown in red, associated with the edges. And then the task of the streaming algorithm ingesting the stream will be, at the end of the stream, to point to one of the cycles and say what the sum of the bits on the edges of the cycle was. Okay. To make this simple, we assume that the edges of the cycles are that have arrived so far at every point in time are posted on a board for all the subsequent, for the streaming algorithm to access. The bits are the objects that one needs to spend space storing. Good. So here's an example. Maybe this edge arrives first with a bit of 1 written on it. Then the edge stays on the board, the bit is erased. Another edge appears, the bit written on the edge is 1. Edge stays on the board, the bit is erased. Another edge appears with a bit of 0, and this proceeds. So the structure of the cycles is essentially slowly revealed to the outcome. Okay, good. And so now we have received the entire graph. Okay, to be precise, it is I have to make the IDs of the vertices appearing in the stream uniformly random, because otherwise the structure of the cycles is very apparent. So really the vertices are equipped with random vertex IDs, and an example stream that happens is the following. For example, you first see an edge E1 that connects vertex 234 to vertex 345, and the corresponding bit is 0. Then another random edge appears, etc., etc. So this proceeds, and we want to understand what the space complexity of streaming cycles is. Good. So let's just design a simple protocol for it. And this protocol will be exactly of the type that I alluded to at the very beginning. Namely, it will be a protocol that stores a adaptively chosen subgraph. The simple protocol is I pick a vertex of my choosing, let's say my favorite vertex, vertex 1. Here it is, the green dot on the slide. And then I simply carry one bit of information. It will be the parity of what I think is the connected component that my green vertex is in. The first edge arrives, it's incident on my vertex, so clearly part of my connected component, I add it to the counter. Next edge arrives, is clearly not, is probably not part of my connected component, but who knows? So I ignore it. I don't know that it is, I ignore the next edge as well. Fourth edge arrives, it extends my connected component, so I add it to my counter, and I proceed like that. Okay, so in this case, I get lucky. Indeed, the connected component that my vertex belonged to arrived in a collectible order. So whenever an edge of this component arrived, I knew that this edge was in my connected component, so I succeed. But I don't always succeed. For example, if my favorite vertex were vertex 10, so here's the green dot pictured on the slide, then I will fail. And here's why. Let's say the first edge from this component arrives, I add 1 to my counter. The next edge arrives, but it does not extend my component. I do care about this edge, but it's not clear to me at this point. So I ignore it, and the game is lost. So in this case, the problem is that the second connected component emerged from 2 cycles that were merged together throughout the process. Good. Okay. All right. So what is the success probability of this protocol? A moment's contemplation reveals that the success probability of the protocol is inverse factorial in the length of the cycle. Why is that? Well, for example, there is one very obvious good collectible order of a cycle is I start with vertex 0, and then the edges in the cycle arrive in the right order, 1, 2, 3, 4, 5 through L. So I just loop around the cycle, and I always know to collect the edge whenever it arrives. Okay, so that happens with probability 1 over L factorial. That's 1 ordering out of L factorial orderings. There are more good collectible orderings, but only an exponentially larger number. So one can verify that this is still 1 over beta L factorial. Good. Okay, good. So now how do I turn this algorithm into an algorithm that succeeds with high probability, well, just don't do it from one vertex. Simply sample L to the order L seed vertices and maintain connected components from out of all of them. At least one will succeed with high probability. So we show that this is tight up to constant factors in the exponent. And so the communication complexity of streaming cycles is L to the omega L. So the factorial dependence is needed. Good. So before I say a couple of words about how this proof goes, let me show you the implications. And the implications, as advertised, are for component finding in randomly ordered streams and for random walk generation in randomly ordered streams. So here's a reduction. Suppose that I have a good component, low space component finding algorithms. I can take a streaming cycles instance and turn it into a graph as follows. So I take a cycle from streaming cycles, the one shown on the left. Note that the edges are equipped with bits. They're all 0 at the moment. This cycle I will turn into either either 2 cycles of length L or 1 cycle of length 2L as follows. So this is a fairly standard reduction as far as reductions in this area go. For every vertex on this, for every vertex I in the streaming cycles instance, I will have 2 vertices I0 and I1, the 0 and the 1 copy. And whenever an edge ij arrives, I connect the 0 copies and the 1 copies if the corresponding bit is 0, and I cross otherwise. So I connect the 0 copy of I to the 1 copy of j, and the 1 copy of I to 0 copy of I. So I claim that if the parity of the bits over the cycle is 0, then I get 2 disjoint cycles of length L. Otherwise, I get 1 cycle of length 2L. And indeed, it is true by observation on the slide when all the bits in streaming cycles are 0. If we flip 1 bit, then the 2 cycles on the right merge, and this stays true for any setting of bits. Okay, great. Good. So this is my reduction. Here's what I get now. Well, first, I get the following corollary from my hardness proof, showing that component finding requires space x factorial in omega L. Right. Good. One recalls at this point that the result of Peng and Zoller from Soda 18 that I mentioned before uses space L to the order L cubed. So this seems good but not tight. We show, in fact, that it is possible to solve component finding and component counting in L to the order L space. So this factorial dependence is tight. Good. Now, the other corollary that we get is for random walk generation. Specifically, suppose that I have a streaming algorithm that generates an exponentially large in L number of random walks of length L, given a randomly ordered stream. Well, then at least one of these walks will loop around the cycle. And recall that in my reduction, I get cycles of length at most 2L. Every component is a cycle of length at most 2L. So at least one of these walks will completely loop around the cycle. So given the transcript of the walk, I will know the size of the connected component that the walk was walking around on. So I can take this connected component, map it back to my streaming cycles instance, and I will know the parity. Okay, so then we get that generating an exponentially large in L number of random walks in a random stream requires L to the omega L space, so factorial in L space. Doesn't quite match the known upper bound, but at least establishes that exponential dependence is needed. Okay, there's one thing that I sort of brushed under the rug in this discussion, which is in which distribution on the orderings does this apply to? And one notes that while the arrival order in the streaming cycles problem is random, the reduction that I proposed actually creates some amount of correlation, because for every stream in the streaming cycles problem I was generating, for every edge in the streaming cycles problem, I generated 2 edges in my graph stream. Okay, good.
Michael, there's about 2 minutes.
Yes, exactly, yes. So let me just say that that is not ideal. We would generally prefer to have a reduction that preserves the random order streaming property, but we can verify. This lets us ask the following philosophical question of, why do we study random order streaming, and whether random order streaming algorithms sort of overfit to this very strong assumption. And we show that they don't. And we do this by defining a model that allows for limited hidden correlations in the stream, in the arrival order of the stream. And we call this model the hidden batch streaming, random order streaming model. And our reduction applies to the hidden batch random order streaming model, establishing a tight result in this setting. Along the way, we show that existing random order component counting algorithms do not really overfit to the assumption much, and they stay robust even if some limited amount of unknown correlations is present. So that's a nice, nice side effect. Good. So just in the remaining 2 minutes, one word about the analysis. Right, and so here's the problem again. The main thing to note here is that the methods for transforming Fourier analytic proofs into analysis for multi-party games, multi-party communication problems, do not work here at all, because the previous techniques that I talked about only apply to settings with a constant number of parties. One can note, however, that in streaming cycles, it is not possible to partition the stream into fewer than n to the omega 1 over L players. So you do need like a large, say, polynomially large if L is constant number of players. Otherwise, just one of the players will know the entire cycle and will know the answer. And in general, one does need techniques here that do not lose anything in terms of the number of players, because the lower bound that we're proving is just significantly smaller than the number of players in the communication game. And we indeed design techniques, Fourier analytic methods, to sort of analyze these, so to speak, continuous communication problems. Good. So just a few words about some nice open problems. For example, note that presently known lower bounds for approximating max cut do not really rule out the possibility of approximating max cut values of non-trivial bipartiteness testers in sublinear in n space with a polylogarithmic number of passes. Somehow it seems that this should be possible and would be fantastic to do this. And there's lots of other exciting open problems. Okay, thanks a lot for your attention.
Questions? So while the audience gathers their thoughts, I have a question about max cut on random order, single pass streaming. Do you think there's anything sublinear there?
Max cut on random order single pass. No, I don't think so. Basically, our work with the Dmitry criterion, I think, extends quite easily to a lower bound, to a linear lower bound.
So you think the lower bound actually extends in this case?
Yeah, I think it's a matter of writing.
Okay, all right. So we'll take bets on that. Any other questions here?
Hey, Michael. Hi, this is Santoshni. I have a question regarding your first open problem. So just to understand it, see if I understand it right. So if you consider the hard distributions like, random bipartite graph versus random graph, like if you given polylog and passes, definitely this should be distinguishable. But yes. Is your question more like, is there a general algorithm that can be like half approximation?
Exactly, yes, exactly. So basically these, the lower bound instances that we get in these reductions, right, they are, they're basically random bipartite graph versus random non-bipartite graph, and you just do collision counting. Basically, you just run entropy 1/2 random walks of length log n, check if they collide, and you know the answer. But is it possible to make n to the 0.99 queries to a general graph and approximate max cut to a factor better than a half?
Fair enough. Yeah.
Or do that in streaming? I feel like it seems probably more of a query complexity question, right? But could also be a streaming question.
Sounds good. Thanks.
Any other questions here?
Hi, Michael. This is Samson.
Hey, Samson.
I had a question about whether these techniques could be applied in general for multi-pass lower bounds. It seems that there is some kind of inequality between the players, so that one-way communication is preferred, and if you're allowing Bob to talk back to Alice, Bob can just give the matching to Alice. Do you see a way to extend these techniques to multi-pass, like even constant number pass lower bounds?
Yeah, okay, great question. Right. I don't as of now. So I think, you see, so the Fourier and basically the communication problems are inherently one way, but the corresponding graph streams are probably still hard, right? You basically, I don't know how to distinguish between a random bipartite and a random non-bipartite graph of constant degree and 2 passes, 3 passes, or anything of this nature. So I think it would be great to somehow, maybe one shouldn't use the same communication problems. I think there was a really nice work by Separ Sadi, Gilad Kol, Raghuvansh Saxena, Huacheng Yu, and I may have missed one of the others, that does something similar for the gap cycle counting problem, which has been the standard application of Boolean hidden hypermatching. They basically prove directly that the corresponding graph streams are hard. Something like that would be fantastic to do here. I'm really curious, maybe one way to do this is say, what is the information theoretic analog of the convolution theorem? Right? So can one somehow learn to apply these techniques or use the same invariants directly on the graph stream? I think that's a fantastic question. I don't really know how to solve it.
Okay, we'll hold off on remaining questions. Thank Michael again.
Thanks a lot.